Hello and welcome to our second differential equations class. This week we're going to finish chapter 1 and start talking about chapter 2. We'll talk about classifications and first order linear equations, first order separable equations. If a differential equation has only ordinary derivatives, then the differential equation is called an ordinary differential equation. In this course, I'm going to be abbreviating ordinary differential equation by ODE. For example, two of the equations that we looked at last week, the falling object equation and the mice and owls equation, have an ordinary derivative in them, so these are ordinary differential equations. If the derivatives in a differential equation are partial derivatives, then the equation is called a partial differential equation, or PDE. For example, these two equations, an equation which is called the heat equation and an equation called the wave equation, are PDEs. The heat equation describes the way that heat moves in, for example, a metal bar. The wave equation describes how waves move in, for example, a guitar string. If there's just one unknown function that we want to find, then one differential equation is enough. But sometimes there might be two or more unknown functions, and for those we would need a system of differential equations. In your linear algebra course you studied systems of linear equations. In this course we're going to be studying systems of differential equations. The order of a differential equation is the order of the highest derivative. For example, the falling object equation and the mice and owls equations were first order ordinary differential equations. This equation, d squared y dt squared plus dy dt plus y is equal to 0. We look to see the biggest derivative. The biggest derivative in this equation is 2. So this is a second order differential equation. Another example. This equation has y triple prime plus 2e to the power t y double prime plus y prime is equal to t to the power 4. The biggest derivative in this equation is the third order derivative at the start, so this is a third order differential equation. In your linear algebra course, you would have studied linear and nonlinear equations. We can classify differential equations as linear or nonlinear as well. Differential equation is called linear if it's a linear function of y and the derivatives of y. One thing to remember here is we don't care about t. We don't care if we have a linear function of t or not. We only care about y and the derivatives of y. This means that a linear equation looks like equation 1, or could be rearranged to look like equation 1. We can have any function of t, doesn't matter, and then one y term, plus any function of t plus one y term, plus dot dot dot, plus any function of t, and then just one y on its own is equal to any function of t. If we take an equation, we can imagine that we replace every function of t by the number 1. So let's just imagine that we get rid of all of these functions of t. And let's imagine that we get rid of all of the derivatives. The question is, do we have y plus y plus y plus y plus y plus y is equal to 1? If the answer is yes, then we have a linear equation. If we have something else, if we have y squared or sine y or e to the power y or anything more complicated than just y plus y plus y plus y, then the equation is non-linear. For example, the falling object equation is a linear equation, and the mice and owls equation is a linear equation. A differential equation which is not linear is called non-linear. For example, y triple prime plus 2e to the power t, y double prime plus y prime is equal to t to the power 4. Ignore all of the functions of t and just look at the y and the derivatives of y. As I've shown in orange, we have y multiplied by y prime. It's not y plus y plus y plus y, it's more complicated than that. So this equation is non-linear. I'm going to show you some differential equations, and for each of these equations I'm interested in finding the order of the equation and in deciding if it's linear or non-linear. For this equation, the biggest derivative is 5. So this is a fifth order differential equation. Is this linear or non-linear? We look to see where are the y's. We have a derivative of y that's on its own plus 2 times a derivative of y, that's okay so far, plus a derivative of y, minus y, minus e to the power x, but we don't care about x, so ignore e to the power x. Derivative of y is equal to a number. All of the y's are separate. There's one y term plus one y term plus one y term plus one y term plus one y term is equal to a number. So yes, this equation is linear. Another example. D cubed y dx cubed plus cos of dy dx is equal to sine x. What is the order of this equation? The biggest derivative is 3, so this must be third order. Is this linear or non-linear? We start with a derivative of y that's on its own, that's okay so far, but then we have cos y. Cos is not a linear function, so this is not a linear equation. This equation is third order and non-linear. What about the third equation? What is the order of the third equation? The answer is this is a third order equation. We have 3 derivatives and 1 derivative. The biggest of these numbers is 3, so this is a third order equation. In the next poll, I'm going to ask you, is this equation linear or non-linear? So far this is almost equal. Remember, we don't care about the x terms, we only care about the y terms. So we can forget about the cos x and we can forget about the sin x. We're only looking at the y terms. The answer is this equation is a linear equation. Forget about cos x, forget about sin x, we don't care about x, we're only looking at y. Forget about all of the derivatives. What are we left with? We're left with y plus y. So this is linear. Y double prime minus y squared is equal to x squared. This is a second order equation because the biggest derivative is 2. But is this linear or non-linear? Yes, correct. It's non-linear because of the y squared term. And one more. E to the power x, 7 derivatives of y, minus x cubed, 99 derivatives of y, plus 2x to the power x, y triple prime, minus x squared, e to the power sine x is equal to 2021. What's the order of this equation? Yes, we have a winner. This is a 99th order equation. But is this linear or non-linear? We don't care about x, so forget about e to the x, forget about x cubed, forget about 2x to the power x, forget about x squared e to the power sine x, forget about 2021. What are we left with? There's one y term minus one y term plus one y term is equal to a number. This equation is 99th order and it's linear. Chapter 2 is about first order differential equations. In this chapter, we're going to be studying equations of the form dy dt is equal to some function of t and y. And the first type of first order equation we're going to study is linear equations. As we've just talked about, the equation is linear if it's a linear equation in y. We don't care about t. So this equation is linear if and only if the function f is a linear function of y. We've seen some linear equations already. Last week, we studied equations of the form dy dt is equal to some number minus ay plus some number b. In this chapter, we're going to generalize this. Instead of numbers a and b, we're going to have functions p of t and g of t. We know how to solve equation 3. Let me go through very quickly, just to remind you. We take equation 3. We rearrange this so that all of the y terms are on the left and all of the t terms are on the right. And then we're allowed to integrate. And if we go through the calculation, we find that the solution is y is equal to b divided by a plus some constant c e to the power minus 80. So for example, if a is 2 and b is 3, then the solution is y is equal to 3 over 2 plus some constant e to the power minus 2t. Unfortunately, this method can't be used to solve the equation with functions p and q. So p and g. So we're going to need to use a different method. And the method I'm going to show you now comes from Leibniz. The idea is, step 1, we need to find a special function called an integrating factor. For the integrating factor, we're going to use the notation mu of t. We're going to multiply the differential equation by this integrating factor, and then step 3, we're going to integrate. For example, use an integrating factor to solve the equation dy dt plus 2y is equal to 3. We already know the solution to this equation because we used the method from week 1. Now we're going to use the new method. We're going to use the integrating factor method. First, we need to find the special function mu of t. We don't know what it is yet, but let's just say it's an unknown function, and we'll multiply the equation by mu t. So we get mu t dy dt plus 2 mu ty is equal to 3 mu t. How can we find a special function mu t such that the left side is integrable? Note that by the product rule, the derivative of mu multiplied by y is mu multiplied by dy dt plus d mu dt y. And compare that with what we have. In green, there's mu t dy dt in both of these. And then we have this orange term, 2 mu up top. Down here, we have d mu dt. If we can have these the same, then we can use the product rule. We want to choose our special integrating function mu t such that d mu dt is equal to 2 mu. We know how to solve this equation. We can use the method from last week. We can separate the variables. We can move all of the mu terms to the left, all of the t terms to the right, integrate and rearrange. And we find that we want mu t is equal to a constant e to the power 2t. This is the general integrating factor. This is every integrating factor which will work. But we don't need every integrating factor. We just need one integrating factor which works. That means we can choose whichever value of the constant c we want as long as c is not 0. And because I like easy numbers and I like easy functions, I'm going to choose c is equal to 1. So we're going to use the integrating factor mu t is equal to e to the power 2t. Now that we know our integrating factor, we can solve the differential equation. We take our differential equation and we multiply it by e to the power 2t. And then, because we've chosen mu carefully, we can use the product rule. The left side of these two equations are the same. They are both the derivative of e to the power 2t multiplied by y. Now that we've done this, we can integrate. The integral of the derivative of e to the power 2ty is just e to the power 2ty. That's easy. When we integrate, we just delete the derivative. And on the right-hand side, again, an easy integral. The integral of 3e to the power 2t is 3 divided by 2e to the power 2t. And because we're integrating, we have to add on a constant. Finally, divide by e to the power 2t, and we get the solution. The solution to the differential equation is y is equal to 3 over 2 plus some constant e to the power minus 2t, which of course is the same solution that we found using the previous method. For the differential equation dy dt plus 2y is equal to 3, we want to use the integrating factor e to the power 2t. Let's suppose we want to use an integrating factor to solve dy dt plus ay is equal to b for some numbers a and b. We could use the same method that we used before, go through the calculation, and we would find that the integrating factor that we want is e to the power at. I'll leave this for you to check. Let's make this a little bit harder. Now let's suppose instead of a number b, we have some function g of t. And as before, we're keeping a here. The integrating factor that we use only depends on the coefficient of y. It doesn't depend on gt, it only depends on what we have in front of the y. So again, we want to use the integrating factor e to the power at. We take our differential equation and we multiply it by e to the at. We have e to the power at dy dt plus a e to the aty is equal to e to the at gt. Using the product rule, this is the same as ddt of e to the power aty is equal to e to the at gt. Now we can integrate. When we integrate the left side, the derivative just disappears, and we end up with e to the aty is equal to the integral of, and just to avoid confusion, I'm changing dummy variable here to s, the integral of e to the power as g of s ds, and then, of course, plus a constant because we're integrating. Divide by e to the at, and we have our general solution. y is equal to e to the minus at, integral of e to the asg of s ds plus c e to the power minus at. An example. Solve the initial value problem. dy dt plus half y is equal to 2 plus t, with the initial condition y of 0 is equal to 2. Here, the constant, which I've shown in red, is a half. Straight away, we know which integrating factor we want to use. We want to use e to the power a half t. We multiply our differential equation by the integrating factor. We use the product rule to simplify it, and then we integrate. And we end up with e to the power t over 2y is equal to 2t, e to the power t over 2 plus some constant c. I will leave this for you to check. Here I've used integration by parts, where u is equal to t and v is 2e to the power t over 2. Please, if you're re-watching this video, please pause here and check that you're happy with this calculation. Divide by e to the power t over 2 and we find the solution. So we find the general solution to the differential equation. Yt is equal to 2t plus c e to the power minus t over 2. But we're not just solving a differential equation, we're solving an initial value problem. That means we need to find the value of c which satisfies the initial condition. We want y of 0 to be equal to 2. This means we need to choose c is equal to 2. And we have the solution. Y of t is equal to 2t plus 2e to the power minus t over 2. IVP, I'm using as an abbreviation for initial value problem. Next example I'm leaving for you to do. Solve dy dt minus 2y is equal to 4 minus t. If you re-watch this, or if you're reading the lecture notes, pause the video or get a bit of scrap paper and solve this problem and just check that the answer is minus 7 over 4 plus t over 2 plus c e to the power 2t. Now let's make this more difficult again. Now let's suppose instead of some number a, we have a function p of t. We need to find an integrating factor which works for this equation. And let me give you a warning, a mistake which students often make. Lots of students think that the integrating factor will be e to the power t, pt. This is wrong. The integrating factor is not e to the power pt, as I will show you. Let's start as we did before. We'll take the equation and we'll multiply it by some unknown function mu. We're looking at mu dy dt plus pt mu y is equal to mu g. As before, the left-hand side looks like the derivative of mu multiplied by y. In green, we have mu dy dt in both equations. In orange, we have p mu in the first equation, d mu dt in the second equation. We want these two to be the same. So we want to choose the special function mu so that d mu dt is equal to p multiplied by mu. And as before, we know how to solve this. We separate the variables, moving all of the mu's to the left, all of the t's to the right, and then we integrate and rearrange to find that mu t must be c multiplied by the exponential of the integral of p of t dt. We can choose any non-zero constant that we want. We don't need to find every single integrating factor which works. We just need to find one integrating factor which works. So it's okay to choose c is equal to 1. And we find that the integrating factor that we want is not e to the power pt, instead it's e to the power integral of pt. As soon as we know mu, we can use the product rule and then integrate and rearrange to find a formula for the solution to this equation. This is the formula for the solution to any linear equation. Typically, we don't use this formula. Typically, we go through the calculation each time. For example, solve t y prime plus 2y is equal to 4t squared with the initial condition y of 1 is equal to 2. First thing to note is our equation doesn't look like the equations that we had before. Before, we always had y prime plus p of t y is equal to gt. This time we have this extra t at the start. First thing to do is to rearrange the differential equation so that it looks like the standard equation that we know how to solve. So the first thing to do is we divide by t, and we're going to be studying the equation dy dt plus 2 over ty is equal to 4t. Here our function pt is 2 over t and gt is equal to 4t. To find the integrating factor, we just use pt. The integrating factor is the exponential of the integral of 2 over t dt. That's e to the power 2, natural logarithm of the absolute value of t, which simplifies to t squared. We want to take our equation and we want to multiply by t squared. And if there's any confusion, when I say you take our equation, I mean this equation. We're going to take this equation, which I've pointed to with an arrow, and we're going to multiply it by t squared. We obtain t squared, dy dt plus 2ty is equal to 4t cubed. Because we've chosen the correct integrating factor, we can use the product rule on the left side, because the left-hand side is just the same as the derivative of t squared y. And then we can integrate, divide by t squared to find the general solution to the differential equation. There's one step left. We need to choose the value of the constant which satisfies the initial condition. You can check that in order to satisfy y of 1 is equal to 2, we need to choose the constant c is equal to 1. So the solution to the initial value problem is y is equal to t squared plus 1 over t squared. Here's a graph of this function shown in red. Every blue curve on this graph is a solution to the differential equation. The solution to the initial value problem is the solution which satisfies y of 1 is equal to 2. In other words, it passes through the point where t is equal to 1 and y is equal to 2. Let me make some comments. Note that this solution is a differential function with domain the open interval from 0 to infinity. The solution becomes unbounded and asymptotic to the y-axis as t decreases to 0. T decreases to 0 is another way of saying t tends to 0 from the right. Why does this happen? This happens because the function pt, or 2 divided by t, has discontinuity at t equal to 0. The function t squared plus 1 over t squared, but for t strictly less than 0, is not part of the solution to the initial value problem. The solution to our initial value problem only exists for t between 0 and infinity. You'll also note from the graph solutions for which the c is strictly greater than 0, in other words, they satisfy the initial condition y of 1 is strictly greater than 1, are asymptotic to the positive y-axis as t decreases to 0. But solutions with negative constant c, in other words, the initial condition y of 1 is strictly less than 1, are asymptotic to the negative y-axis as t decreases to 0. This means there's some special initial value, in this case y of 1 is equal to 0. That's a mistake, it should be y of 1 is equal to 1, where the behavior changes. This is called a critical initial value. I'm going to go back to look at the graph. These solutions up here are going up to plus infinity. These solutions are going down to minus infinity as t decreases to 0. And in the middle, there's a special solution, in this case, y is equal to t squared, which separates these two behaviors. Our final chapter for today is separable equations. Go back to the general first order ordinary differential equation, or dy dx is equal to f of x and y. In the previous section, we've looked at a special case of first order equations called linear equations. In this section, we're going to study another special case of first order ordinary differential equation. Equation 7 can always be written in the form m of x and y plus n of x and y dy dx is equal to 0. There's an easy way to do this. We could just choose m is equal to minus f and n is equal to 1, and then rearrange, and we get equation 8. But of course, there may be other ways we can rearrange equation 7 so that it looks like equation 8. Sometimes it's possible to do this such that m of x is a function only of x and n of y is a function only of y. Sometimes it's possible to rearrange equation 7 so that it looks like m of x plus n of y dy dx is equal to 0. If we can do this, then the equation is called separable. It's called separable because we can rearrange m of x plus n of y dy dx equal to 0 to m of x dx is equal to minus n of y dy. It's possible to rearrange our equation so that all of the x terms are on one side of the equal sign and all of the y terms are on the other side of the equal sign. In other words, it's possible to separate the variables with an equal sign. For example, consider dy dx is equal to x squared divided by 1 minus y squared. Show that this differential equation is separable and solve this differential equation. We can rearrange this equation to minus x squared plus 1 minus y squared dy dx is equal to 0. we have a function only of x plus a function only of y, dy dx is equal to 0. This is the same as of the same form as equation 9. So this equation, the equation at the top or the bottom equation, is a separable ordinary differential equation. Now note that the derivative of minus 1/3 x cubed is minus x squared, and the derivative with respect to y of y minus 1/3 y cubed is equal to 1 minus y squared. So our differential equation is the same as x derivative of minus 1/3 x cubed plus y derivative of y minus 1/3 y cubed dy dx. Look at the second term. We can simplify this using the chain rule. Remember, the chain rule says, for example, du dx is the same as du dy dx. And this is the sort of thing we have. We have d dy of some function multiplied by dy dx. So this orange function is the same as d dx of y minus 1/3 y cubed. Our equation is the same as d dx of minus 1/3 x cubed plus 1 minus 1/3 y cubed is equal to 0. And this is easy to solve. We can just integrate. Integrate the left side, the derivative just disappears. Integrate 0, we have some constant. Minus 1/3 x cubed plus 1 minus 1/3 y cubed is equal to some constant, capital C. Or we can multiply by minus 3 if we want. Change capital C to a new constant, small c, which in this case is minus 3 multiplied by capital C. And we have our solution, x cubed minus 3y plus y cubed is equal to c. We can use this method to solve any separable first order ordinary differential equation. Let's consider the general first order separable equation, m of x plus n of y, y prime is equal to 0. And let's suppose that we've found two functions, h1 of x and h2 of y, which satisfy that the derivative of h1 is equal to m and the derivative of h2 is equal to n. Then our differential equation, in fact, is the same as the derivative of h1 plus the derivative of h2 dy dx is equal to 0, or by the chain rule, the derivative of h1 with respect to x plus the derivative of h2 with respect to x is equal to 0. Integrating gives the solution h1 plus h2 is equal to c. So to recap, to solve mx plus ny y prime is equal to 0, we need to integrate m with respect to x, and we need to integrate n with respect to y. But this is basically what we were doing last week. When we used the method I showed you in chapter 1, the method I said that pure mathematicians didn't really like, we rearranged our equation so that all of the x terms are on the left and all of the y terms are on the right, and then we integrated. We integrated m with respect to x, and we integrated n with respect to y. So basically, we were doing the same thing last week. You can use whichever method you wish. You can use the method from week 1, which pure mathematicians don't like, or you can use the method that I just showed you, which is the one that pure mathematicians really want you to use. I don't care which method you use. For example, solve dy dx is equal to 3x squared plus 4x plus 2 divided by 2, y minus 1, with the initial condition y of 0 is equal to minus 1. We can rearrange our differential equation to 2y minus 1 dy is equal to 3x squared plus 4x plus 2 dx. I've moved all of the y terms to the left and all of the x terms to the right. Because the x and y terms are separated, we are allowed to integrate this equation. Integrating gives y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus c. We need to find the constant c. We use the initial condition y of 0 is equal to 1. Just here. So instead of y squared, we have minus 1 squared or 1. Minus 2 multiplied by minus 1 is the same as plus 2. Replace every x by 0. We have 0 plus 0 plus 0 plus c. And then we see that c must be equal to 3. So we have the solution to the initial value problem. Y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus 3. An equation like this, where we have some complicated function of y instead of just y is equal to a function of x, is called an implicit solution. Sometimes this is the best type of solution that we can find. If that's the case, that is the answer to the problem. But in this example, it's possible to simplify our implicit solution. It's possible to solve for y. Because y squared minus 2y minus x cubed plus 2x squared plus 2x plus 3 equal to 0 is a quadratic equation. We know how to solve quadratic equations. We know how to solve, for example, AR squared plus BR plus C equal to 0. We know that R is minus B plus or minus the square root of B squared minus 4AC divided by 2A. So we know that y must be 1 plus or minus the square root of x cubed plus 2x squared plus 2x plus 4. Before we go on, this 4 at the end is not a mistake. If you go through this calculation and check this, you will find that this number shouldn't be a 3. It's correct that we have a 4 just here. Please check that for me. There's 2 solutions here, but only one of these solutions is correct. There's 2 solutions because we could have plus or we could have minus. Each one of these solutions gives us y of 0 is equal to minus 1. Should we have plus or should we have minus? I want y to be minus 1 and I want x to be 0. So we have minus 1 is equal to 1 plus or minus the square root of 0 plus 0 plus 0 plus 4. Do we have plus or do we have minus for this to be correct? The answer is minus. If we have y is minus 1 and x is 0, we want to satisfy minus 1 is equal to 1 plus or minus the square root of 4, or 1 plus or minus 2. For this to be correct, we must have minus 1 is equal to 1 minus 2. The answer is we want the solution with minus. So the solution to the initial value problem is y is equal to 1 minus the square root of x cubed plus 2x squared plus 2x plus 4. If we can find a solution like this, a solution where y is equal to some function of x, we have a solution which is called an explicit solution. An implicit solution is a solution where x and y are all mixed up, or some complicated function of y. If it's y is equal to a function of x, we have an explicit solution. If possible, we prefer explicit solutions, but sometimes it's not possible to find an explicit solution. So then the answer to the problem would be an implicit solution. Here is a graph of this solution. You can see that the function, which I've shown here in red, starts at minus 2 and goes all of the way to the right. The domain of this function is from minus 2 to infinity. The top part of this curve, which I'm going to show in purple now, is the solution with plus. The solution with plus doesn't pass through 0 and minus 1, so it doesn't satisfy y of 0 is equal to minus 1. For example, solve dy dx is equal to y cos x divided by 1 plus 2y squared with the initial condition y of 0 is equal to 1. Here's the whole calculation. First, I want to rearrange the equation so that all of the y terms are on the left and all of the x terms are on the right. We get 1 plus 2y squared divided by y is dy is equal to cos x dx. Because all of the y terms are on the left and all of the x terms are on the right, we're allowed to integrate. So we're allowed to add these orange integral signs on both sides. The integral of 1 plus 2y squared over y is the natural logarithm of the absolute value of y plus y squared, and the integral of cos is sine. Don't forget that when we integrate, we have to add on plus c. Using the initial condition, we have log of 1, which is equal to 0, plus 1 squared is equal to sine of 0, which is 0, plus c. So the constant must be 1. The answer to this problem is the implicit solution, natural logarithm of the absolute value of y plus y squared is equal to sine x plus 1. We can't solve this for y, so we're going to leave this as an implicit solution. What can we say about the solution? We can say that if y is equal to 0, then the left-hand side is minus infinity because of the logarithm term, but the right-hand side is between 0 and 2. This means that it's not possible for us to have y equal to 0. We know that y of 0 is equal to 1. So we know that the function is strictly positive at least 1 point. We know that the solution will be continuous. That means that y must be strictly positive for all of the x in the domain of the solution. It's also possible to show that the solution exists, or the domain of the solution is the whole real line. But I'm leaving this for you to think about. And that is the end of today's lecture. Next week, we're going to talk about the differences between linear and non-linear first-order ordinary differential equations. And we'll study another special type of first-order equations called autonomous equations, which we will use to talk about population dynamics. Before I go on, homework 1 is available. If you look in the left menu, you'll find a link called homework. Scroll down, you will find homework 1. Written in blue and underlined is a PDF file, 2020 to 21, differential equations, homework 1.pdf. This file contains the questions for homework 1. Load this first, print it out if you wish, and solve your problems. After you've found your solutions, you start a multiple choice test by clicking on the title homework 1, and you enter your answers into the system, and you will find out straight away if you are correct or not correct. You can have 3 goes at each homework. So if you find that some of your answers are incorrect, you can have another go. The deadline at the moment it's set to the 10th of June. If necessary, I can extend that to 1 day before the final exam, because I want to use this homework to help you prepare for the exams. That means if you really, really want to, you could wait till June before you do the homeworks and then do all of the homeworks together. But I think this would be a bad idea. Most people learn mathematics by doing a little bit each week. So while I leave it completely up to you to decide, my advice is that you should try to do 1 homework each week. Are there any other questions? So the way my lessons work is, once I get to this orange screen at the end, you're welcome to ask questions. If you don't have any questions, you're welcome to leave whenever you wish.